Okay, grade 12. Today we're going to look at rate laws and how to determine a rate law. We're going to use a method called the initial rates method, and that's where we're actually going to have some data to figure out our rate laws. What is a rate law? Well, rate law is just simply a mathematical equation so we can actually calculate rates of reactions. It will show us how the rate is related to the concentrations. Remember that if you have more concentration of things, typically you'll have more collisions and a faster rate of reaction. So the rate laws are going to allow us to do that. So rate laws are expressions which relate the rate of reaction to concentration. It allows us to calculate the rate of reaction with the given concentrations of reactants. So if I know the rate law and I know what the concentration of my reactants are, I can figure out how fast that reaction is going to go right off the hop. It basically now allows us to put quantitative numbers, actual quantities, amounts to our concentrations and rates. These memes will make sense in a few minutes. So if we have a reaction A making some sort of products, who cares what the reactants and products are? We just have reactants making products. Our average rate is going to be the change in A over the change in time. And you would see that if I make A bigger, so like if I changed A and I made the concentration of A really big and time the same, then my rate gets bigger, right? Because a bigger numerator gives you a bigger quotient. The faster A is consumed, the lower the concentration. So as A is used, then the A gets smaller and smaller and smaller, and that means rate's going to get smaller and smaller and smaller. We can represent that direct relationship using an equation like this. We kind of saw direct relationships with gas laws and Boyle's law. Pressure times volume was constant. Well, we can say rate and A, the ratio of rate and A is constant as well. You're going to see this K that talks about it's the rate constant for this reaction. Square brackets around A means concentration of A, and X is a power. It's called the order of the reaction. That's this guy here. We're going to talk about what the order of the reactant is. Today we're all about trying to figure out the powers on each of the reactants. And then we'll talk about rate constant in a second here, but we'll calculate the rate constant tomorrow. So what is the rate constant? Well, it's a constant specific for any reaction, just like with the pressure-volume relationship of gases. That was a constant always. It's just different for different gases. It's specific for every reaction at specific temperatures, and its value always depends on the size, speed, and type of the molecules. If we change our temperature, that's going to change the rate constant. So we always want a specific temperature. The only factor that's ever going to affect any of our constants in a reaction is temperature. That's what I said there. Kind of a big picture item that you're going to see, a big theme that keeps coming back over and over again when we get into equilibrium laws as well. So what is the order of a reaction? Well, it indicates how much the concentration affects the rate of a reaction. And we can only do this, we can only figure it out actually by experimenting. So before I show you how we would do that with experimental data, let's talk about what these orders mean. So if you have a first order reaction, it tells us that the rate is directly proportional to changes in concentration. So I'm going to use my rate law that I had earlier. Rate equals K times A to the power of X. So in this case, it's going to be rate equals K times A to the power of 1. So let's see what happens if we make different concentrations. So you'll get rate equals K times, let's say the concentration was 1. 1 to the power of 1 is 1. So rate is going to equal K times 1 or just K. But if I double that concentration, so let's do this. Rate equals K times 2 to the power of 1. Well, 2 to the power of 1 is 2. 2 times K is 2K. So what we did was we doubled the concentration, the rate would double. If I triple the concentration, so I'm going to go rate equals K times 3 to the power of 1. Well, 3 to the power of 1 is 3 times K is 3K. So I tripled the rate, and so on and so forth. So a first order reaction is one where whatever you do to the amount of reactants, the exact same thing will happen to the rate. So if I put in 10 times more stuff, the reaction will go 10 times faster. That's what makes it first order. But a second order reaction is like exponential growth. So if we double the concentration, it would quadruple the rate. So this is what it would look like. So let's change it to a second order rate, or second order reaction. So it'd be K times A to the power of 2. So let's do our same thing here. So rate equals, let's start with a concentration of 1, so K to the power of 1 squared. 1 squared is 1, 1 times K is K. But if I double the amount of A, so now I have K times 2 to the power of 2. Well, 2 to the power of 2 is 4. 4 times K is 4K. Notice, all I did was double the concentration of A, but the rate quadrupled. It's going 4 times faster. Now let's see what happens if I triple the concentration of A. So rate would be K times 3 squared. So 3 squared is 9. 9 times K is 9K. So if I triple the amount of stuff, the reaction is going to go 9 times faster. So it's a much bigger impact. You can imagine if we had a third order reactant, it would go up way faster because the exponent, that power, this is why we call it exponential growth, is big, so it has a huge effect on our rates. Now, here's the neat thing is you can also have a zero order reaction or a zero order reactant. Now, let's think about what would happen. If we had rate, let's say A was zero order, K times A to the power of 0. Okay, so we'll do our same thing here. So rate equals K times 1 to the power of 0. Well, anything to the power of 0 is 1. So 1 times K is K. Let's double the amount. Rate equals K times 2 to the 0. Well, 2 to the 0 is 1. That's still K. And if I put rate is equal to K times 3 to the power of 0, 3 to the power of 0 is 1. It's still K. It doesn't matter what we do to the amount of reactants. The rate has not changed. It has had 0 effect on the reaction. So here a change in concentration has no effect. Now if I relate this back to mechanisms, which we will later, think about which step in a mechanism has no effect on the rate. Now another way to look at this is just trying to do it graphically or like in a table format. If I double the concentration with 0 order, rate is staying the same. If I triple, this stays the same. So that's 0 order. If we're looking at first order, well, if I double, this doubles. Second order, if I double, this quadruples. And the third order, look at this. If I only double the concentration of a reactant, the rate goes up by a factor of 8. If I only triple, if I only put 3 times more in with a third order reaction, it goes up by 27 times faster. So that's what these orders do. The bigger the exponent or the bigger your power, the bigger effect these things have on their reaction rates. So if we have a reaction that has more than one reactant, our rate law is going to look a little bit different, but we just include all of the reactants because every reaction or every reactant can affect the rate differently. So our rate law would look something like this. This is a generic rate law. It's going to be A times B, and the powers on A and B can be different. They can be the same, they can be different. It doesn't matter. This rate, what this is saying is the rate depends on the concentration of both A and B, and they can affect the rate differently. Now the other thing that we should mention is that the total order of reaction is the sum of your powers, so sum of your exponents in the rate law. So X and Y here would add together to give the overall rate, how all of the reactants together will affect the rate of the reaction. You'll see that at some point. If I ask for the total or overall order, that's what we're looking for. Now, here's how we're going to find our rate laws. We're going to use this initial rates method. It can only be done through experiment, and we can't just figure out rate laws just from the coefficients in the reaction. You'll see why later when we get into mechanisms. But what we're going to do is we're going to take some data and we're going to measure changes in concentration. We're going to change one concentration, see how it affects the rate. We'll change another concentration, see how that one affects the rate. And by doing so, we can see how each reactant independently affects the rate. So here's some data. And if we look at the data, what they did was we have 3 trials. And we're just trying to find out how each of these reactants will affect the rate of the reaction. So from trial 1, like trial 1 is kind of our control, almost, if you will. We started with this concentration, we got a rate. So then we want to see how HI affects the rate. So if you look from trial 1 to trial 2, what they did was they kept H2O2 constant, right? If we want to see how just HI affects the rate. We don't want H2O2 to change. So we're going to hold that one constant, and we're going to double this one. So by doing that, we know that any changes in that rate is caused by HI. And if we look from 0.0076 to 0.0152, that is also doubled. So for HI, we can say, well, it went from the 2, like we doubled the concentration, and we want to see what causes that to make it stay the same. Well, 2 to the power of what is 2? So x has to be 1. 2 to the power of 1 is 2. That means that this is first order. Now, if we want to find out how H2O2 affects the rate, we need to look where H2O2 changes and HI does not. Like, I'll give you an example. This isn't one where we won't look at it. We wouldn't look at these two trials. And the reason for that is I doubled this one and I halved this one. So we changed two things at a time. We wouldn't know which thing caused the change in rate. So we're always going to hold every reactant except for one constant. So to find how H2O2 affects the rate, I'm going to find two trials where H2O2 changes and HI does not. The only two trials where HI does not change is 1 and 3. So that is timesing by 1. It didn't change. But this one times by 2. And if I look, the rate also times 2. So again, same thing. 2 to the power of something gives me a change in the rate of 2. Well, that something is 1. So my rate law is going to look like this. Rate equals K, we'll deal with K tomorrow, times the concentration of H2O2 to some power times the concentration of HI to some power. And what we just did over here is we figured out the powers. This means that this is also first order. So I can get rid of these generic powers and I can actually put in the real powers. It's 1 and 1. Now, obviously in math you wouldn't write a power of 1. I'm just doing that to show you where those numbers are coming from. Let's do another one. So we want to find the rate law for this reaction. It might even help just to start by writing your rate law just generically. So rate equals K times, and the concentration of your reactants, NO2 times F2. Now we want to know what that exponents are, or sorry, the powers, I guess, are. So to find let's start with NO2. So to find how NO2 affects the rate, I want to find two places, or a place where this reactant changes and the other one does not change. So I see that F2 doesn't change from trials 1 to 2. So there we go. Now, this is staying the same, but this is timesing by 5. So I know that any changes over here is caused by that. F2 has no effect on the rate right now because it didn't change, but NO2 did. So this also goes up by 1.2 to 6 is a factor of 5. So 5 to the power of something gives me that change of 5. Well, x equals 1. Now let's find two trials where F2 changes and the other one does not. And I'd like to pick two trials where it's easy math. So I'm going to look here to here, because this is timesing by 1, and this is timesing by 3. Now, that means that any changes in the rate is got to be caused by F2, because NO2 didn't change over those two trials. So this 0.4 to 1.2 is also timesing by 3. So 3 to the power of something gives me that change in rate of 3, so x is 1 again. So these powers, both of these reactants, are first order again. So this is a 1 and that's a 1. And again, normally you wouldn't write those. I'm just trying to show you where they come from. So now try this one. Obviously, we've been doing first orders, so I'm thinking that probably won't be all first orders in this one. Give it a try, see if you can figure out what they are, and then come back and watch the end of the video to see if you got it right. So I'm going to write my generic rate law. So rate equals K, and I'm going to write my concentration of my reactant, CH40S, H2O. And we want to figure out what those powers are. So let's start with the first one. I want to find two trials where this chemical changes and the other one does not. Well, that would be trials 1 and 2, because I doubled this and this did not change. Now, I will know that this change over here is caused by that change. So that doubled. Now 0.182 to to 1.45. Well, that's not such an easy thing to see. So I want to see how do I get, like what do I times by to get from 0.182 to 1.45? So we just take 1.45 and divide it by 0.182, and I got 7.967. So we're saying that's roughly a change or in a factor of 8. So if we double the concentration and the rate octuples, then what power would have to go there? 2 to the power of what is 8? Don't say 4. It's going to be 2 to the power of 3 is 8. So that tells me that this is third order. That means it has a really big, look at, we only doubled that. We only doubled the concentration, but the rate went up by a factor. It went 8 times faster just by doubling the concentration. Okay, remember 2 times 2 times 2 is 8. So that means that CHCl3 is third order. Now I'm going to do the same thing for the other one. We want to find 2 trials where this reactant is constant. So that's trials 2 and 3. This is quadrupling. And let's see what happens here. Well, if you can't see what that change is, we'll take 5.81 divided by 1.45. Oh, that's also changing by a factor of 4. So 4 to the power of something is 4. That something is a 1 again. So this is first order. So that would be your rate law. And that's as far as I'd go today. I would like you to try to figure out how to get all your powers on your rate, like write your rate laws and get the powers on that initial worksheet. And then tomorrow we'll go over how to solve for K.